Okay, let's get started here. So project number 1, it's all written, but I have not posted it to the course website yet. I will post it sometime after class today. And we will discuss it on Monday. So what I recommend is that before class on Monday, read through it. If you really wanted to, you get started on it too. And just be prepared to discuss it in class on Monday. Now, if you remember that these projects I mentioned the first day of class, I know it's been a while. These projects you can work in groups. Let me zoom in a little bit better here. And I know that some of you may not really know anybody else in the class. So what I am going to pass around on Monday is a group sign-up sheet that is meant to, I guess, first of all, for you to declare your group. But second, if you don't really know anybody else in the class, this could be a way potentially that you can find a group. So this is what the group sign-up sheet looks like. So put your name in one of the 4 options. Option number 1, we have formed a group of 2 to 3 people, are not looking to add anyone. So if this is the case, just put your names there, draw a big circle around your name so I know that, draw a big circle around all the names of the people in the group so that I know what group you're in. Option number 2, we are a group of 2 people looking for a 3rd member. I guess also I should mention, because I know it's been a while since the first day of class, you can work in groups of up to 3 people. Okay? So let's say you do have a group. It has only 2 people in it, but you'd be willing to add a 3rd person. Well, write your names in that area there of this sheet of paper. Draw a circle around those 2 group members' names. Option number 3, I would like to be in a group. I am currently not, so just simply sign your name there, and I will try to put you in a group. And lastly, option number 4, I would like to work alone, which is completely fine. If you want to work alone, it's great. Or not necessarily great, but go ahead and do it. I do recommend working in groups because I think you can learn a lot from your fellow group members. So, again, on Monday, I will pass this around, and hopefully then we can get everyone in groups for these projects. Are there any questions about this? Okay. And also, you can always change groups during the semester. So if your project number 1, you were in a group that didn't really work out good, you can always change groups. Let's see. So today we will continue in this graphics section. Are there any questions before we get going in the lecture notes? Okay. So we were talking about bubble plots last time, and essentially what a bubble plot is a scatter plot between 2 variables, and then the plotting point, its size is proportional to a 3rd variable. That's the basic bubble plot. And we looked at bubble plots in the context of the serial data, but when you just look at it in terms of one data set, you don't necessarily have a chance to see all the different kinds of trends that could happen in one of these bubble plots. So what I've done simply is just drawn out 2 different bubble plots to help you see possible trends that could occur so that when you analyze maybe other data sets, you understand what these trends look like. So in particular, this first bubble plot here, notice obviously as x and y increase, as x increases, y increases. But look what also happens in terms of the size of the bubble. How about we call the 3rd variable z? You can see that z is increasing in size as well because these bubbles are growing in size. So essentially what we have here is a 3-way association between the variables. As x increases, y increases, and z increases. Then here's another plot. This is on page 16. Notice there's really no association between x and y in this particular plot. It looks like a random, if you just ignore the size of the plotting point, it just looks like a random scattering of points. But then when you look at the size of the plotting point, you can see that towards the middle values of x or towards the middle values of y, we see increases in the value of, let's say, z. And so we do have a trend that's detected by this plot. Now, if I were to instead draw a plot like this where I have x and let's say z on what we would normally call the y-axis, and I'm not going to worry about y at all, what would you expect this plot to look like? If I were to maybe draw a line.
Quadratic.
A quadratic, exactly, something like this maybe. Why? Well, take a look at this. Here, the values of z are small. The values of z are small. Now in the middle, the values of z are large. And so this is what this bubble plot allows you to see here. And you can say the same thing for y versus z as well. Okay, so those are just other possible trends that you could see in these kinds of plots. Now, an example where bubble plots can be used inside, let's say, a formal data analysis is with respect to regression models and various diagnostic plots. If you've had my Stat 870 and Stat 875 class, you've seen me use these bubble plots before, but obviously I know a number of you have not had before that class. So let's take a look at a quick example of how useful these kinds of plots can be. Now, in a simple linear regression setting, let me pull up a Windows journal here so I have a clean sheet of paper I can write on. In a simple regression setting where you have, let's say, x and y, you might have a scatter plot of points that look like this. And, a simple linear regression line would basically go in the middle of these points like this. Right? Okay. Now, what happens, well, would you say that, first of all, would you say that this model's fit in this data pretty good? Yeah. But let's say instead I have an additional point on here, and I have an additional point on here. Now, would you say that the model's fitting the data well? Perhaps not. So we see some points that are very far from the regression line. And so what you've learned in your first STAT course, like a STAT 801, is that essentially the farther the points are getting from the regression line, the less that the regression line is, let's say, explaining about the variation in y, or the poorer the fit, to some respect, you could say. Okay. So that's what you often look out for. Now let's apply this same idea to a logistic regression context. Now I understand that there's probably some of you who have not seen logistic regression before. Simply with respect to logistic regression, or what logistic regression is, if you haven't seen it before, you can think of it as that you're trying to model the probability of success. So instead of like in a regular regression setting where you have a y that has a normal distribution, essentially your response in a logistic regression setting is binomial instead. And if you think of the binomial random variable, let's call it y, divided by n, your number of trials, that's essentially an estimated probability of success. I'm sorry, that's an estimated proportion of successes. Okay, so now we're going to try to relate independent variables to the estimated proportion of successes. And in particular, the data set that we're going to examine here involves this place-picking data set that we looked at a little bit earlier in the course. And we're going to look at it in a very simple context where in my data set I have the distance of a place pick, such as 18 yards. And at 18 yards I had 1 failure, 2 successes. So the proportion of successes was about 0.67, 2/3, at this particular distance. At a distance of 19 yards, 7 successes, 0 failures, so perfect in this particular data set. If we come all the way down to the end here, a distance of 66 yards, we see 0 successes, 1 failure, so the proportion of successes is 0. What I like to be able to do is use this thing called a logistic regression model to come up with a way to relate distance to this estimated proportion of successes. Okay. Now we will be talking about logistic regression later in the course. So eventually this kind of a plot you'll know how this plot came about. So I'm not going to talk about the details right now. But essentially this red line here is my logistic regression model. Notice on the x-axis I have distance, on the y-axis I have estimated probability of success. And essentially that red line is serving the same role of this red line on this scatter plot of y versus x. Serving the same role. So what I've actually also plotted here is the observed proportion of successes at a particular distance. Ignore the size of the plotting point for now. So for example, remember 18 yards, there was 2 successes out of 3 trials. At 66 yards, there was 0 successes out of 1 trial. Okay. Now, if you ignore the size of the plotting point here and apply what you learn in simple linear regression with respect to how to determine if your fit of your model is good or not, what would you say about the fit of this particular model? Is it good or is it bad?
Looks like it's okay, but there's a few outliers.
It looks like it's okay, but there's a few outliers. Essentially, to some respect, yes. Notice we have some points that are far from the regression line. And if you saw this in simple linear regression, you'd say, uh-oh, I might have a problem here. Okay? But in a logistic regression setting, actually, I'm not worried. Here's the reason why. So remember, let me do some erasing here too. Remember, this point here is 0 successes out of 1 trial. If I had 1 success out of 1 trial, where would that point be? Essentially, up here. So either, if I only have 1 trial at a particular distance, the point is either at the very bottom or at the very top. There's nothing in between. If I come over here to this 18-yard place kick, it was 2 out of 3. So again, where could the point be? Well, it could be right here, 0 out of 3. It could be right here, 1 out of 3. Here's 2 out of 3 and 3 out of 3. So the only way that you could get close to the line is if you actually have 3 out of 3. Well, with binary outcomes, you're bound to miss one place kick. Okay? It's going to happen sooner or later. And maybe this was the sooner case. But I'm not worried about that point there. So I know it represents very few number of trials. Now, what I've done in this plot to help people visualize, well, should I be worried about a point or not, is I've plotted that bubble there to be proportional in size to the number of trials. So that's why you only see like a little speck, you could say, right there, because there's only 1 trial. This point here represents only 3 trials at a particular distance, at the distance of 18 yards. That's why those points are so small. So in this kind of a setting then, what I'm hoping to see is that the points that are larger in size are going to be close to the line. If I were instead to have a point that looks like this right here, that large in size, it was that far from the line, now I would be worried about the fit of my model. But instead, if I just have a simple point that's very small like that, now I'm not worried. And so my whole point of saying this is, again, to show you how useful these bubble plots can be. But now this is in a different context from what we've been seeing so far. Are there any questions? Okay. So let's move on to a new plot. A 3D scatter plot. Essentially take a 2D scatter plot and now put it in 3 dimensions. So you have an x-axis, you have a y-axis, you have a z-axis. We've already seen some 3D plots in the past. When we did the bivariate normal distribution, we plotted a surface. If you remember, we used the RGL package, R graphics library, to get a function that plotted something in 3D. We're going to use the same package here. There's a few other packages in R that one can use for 3D plotting. Why did that do that? There's a few other packages in R that one can use, but none of them are as good as this one. So that's why I'm only going to talk about this one. And we're going to use a function called plot3D. So let me come over here to my program. Plot3D, for my x-axis, I'm going to apply to the serial data. I'm going to put sugar, y-axis fat, and z-axis sodium. And I have arguments like you would see in the plot function, like xlab for x-label. Color of my plotting point is going to be red. And the size of my plotting point, I'm going to choose 6. Basically, this is a little bit odd, but according to the help file for this function, the default is a size equal 3. This again corresponds to the size of the plotting point. And a size equal 3, according to the help, corresponds to a point size on your plot that's 1/20th of the size of your whole plotting area. It's not that big of a deal to know that. I'm not going to ask you on a test. What does a size equal 3 mean? The main thing is that you know that if you increase the size, you're going to get a bigger plotting point. If you decrease the size, you're going to get a smaller plotting point. That's a big thing to understand. And so let me go ahead and execute this code. And similar to what we saw before when we were plotting a surface, this extra window that's essentially kind of outside of R pops up. And you can make the window bigger. You can rotate the plot by left-clicking on the plot and then dragging your mouse. So what we see here again is a 3-dimensional scatter plot of fat versus sugar versus sodium. Now, to some respect, it might be a little bit difficult to figure out exactly where some of those points are actually lying in that area there. So there's 2 little things that you can do to make the plot a little bit more readable. The first thing is that you can put some grid lines on the plot. There's a function called grid3D. You specify, well, what sides do you want the grid lines to be on? Well, how about x, y, and z axes? Okay. What color do you want? We'll say light gray, so it doesn't stand out too much. And this is what we get. So now you have a way to a little bit see better where your points are in that 3-dimensional space. But there's one other thing that you can do to make this plot a little bit more readable. This is shown then also on page 20. Is that you can draw what are called needles. And what needles are is basically from, if you imagine a plane at z equals 0 in terms of the z-axis. If you imagine a plane there, and you're going to draw a line, a vertical line essentially, up to your plotting point. That's called a needle. And that helps you judge where is your point in 3D space. So this is how you can draw one of these plots. Again, plot 3D. The new argument is type equal h. I think of the 8, why it's called h, to mean height. You're going to be drawing basically a line from z equals 0 up to a certain height. That's a way that I think of to remember that. So let me go ahead and draw that. And so now you can see these needles essentially sticking up from z equals 0. But we can make this plot a little bit better by actually putting now the actual plotting point on the plot. By saying again plot 3D, sugar, fat, sodium, but I'm going to add it to my current plot. Color red, size of the plotting point 6. And let's also put some grid lines on it too. And so this is what we get right here. So you can have a little bit of better sense. So for example, if you look at where my mouse is, you can see where this particular point is relative to the z equals 0 plane. You have a better sense of where everything is at in this plot here. If you really want to, you can tip it upside down. I don't know how useful that is, but it's kind of fun to do sometimes. So, anyway, again, why are we looking at these plots? Well, what we want to do is determine particular trends that we may see in these kinds of plots. What do you see here? This kind of corresponds to what we've already essentially discussed for some of the other plots. Remember the shredded wheats? Mm-hmm. The zero sodiums. Look where they're at, right here. And notice as I spin this around, you can see how they are really separated pretty much from all the other points. They are far from all the other points there. We also see some other points that are kind of separated, these right here. And unfortunately, I think I forgot to write them down, but we can figure out which points they are by looking at our bubble plot that we've drawn before. So let me just make sure I get this right. Sugar. These points right up here with respect to the bubble plot. That's what, let's turn it this way, you can see that these points are corresponding to. Okay? So on page 20 then, I asked a question, well, remember we're kind of concerned about the shelf too, shelf 1, 2, 3, 4. How could we add that kind of information to this particular plot?
You can change the plotting point, color, the size, what kind of point the circle.
Exactly. So you could change the plotting point somehow to correspond to shelf. Probably the easiest way is to change the color. From what I've seen with the RGL package and this plot 3D function, you cannot actually change the plotting symbol, which is kind of disappointing. But that's just the way it is. There are other functions out there that you could, but they're not in the RGL package and you wouldn't be able to rotate. Okay, so this is not in the notes, but it is in my program. How we could get then the shelf representing the plot. Suppose I simply take a look at shelf here that's in my serial data frame, and I'm just going to simply pull it out and create a new object called shelf, just to make some of my typing a little bit easier. It's going to be referring to shelf a lot. And then what I'm going to do is actually plot each shelf's nutritional information one at a time. So my first plot 3D is going to correspond to shelf equal 1. Now notice that this here, for my x-axis, I'm going to specify sugar, but this additional part here essentially just pulls out shelf equal 1. Now let's make sure you understand why this occurs. So this is a logical comparison. I think we briefly talked about some of this before. If I take shelf equal 1, what's going to do is look at all 40 items that are in shelf, all the shelf numbers, and look at which ones are equal to 1 or not. You do need double equal there. And it's going to return a bunch of trues and falses. So that then, when I combine that then with the sugar here, what's going to happen then is I'm going to pull out just the items in sugar that correspond to the trues. And so that's shelf 1. So essentially, what happens here is I'm taking 1:10, and I'm just pulling out those first 10 items. Any questions about that?
So shelf doesn't have to be in the data frame that you have for serial.
It doesn't, no.
That's cool.
And yeah, I mean, it doesn't. And in fact, most functions like that, you don't necessarily need to have stuff in a data frame. It's convenient to organize stuff like that. But like if I want to fit a simple linear regression model, if you remember from the intro to R notes, I have the LM function. I don't have to put the stuff into a data frame first. As long as it exists someplace in my R database of data information, that's fine. Okay, so then for my y-axis, I'm going to do exactly the same thing, except for now with fat. And then for my z-axis, do exactly the same thing with sodium. And then you can see I have other plot 3D functions here, shelf 2, shelf 3, shelf 4. All of them contain an add equal true, and all of them have a different color to the plotting point. Now there's one last part here that's very important. The shelf equal 1 cereals, the sugar, fat, and sodium content may not necessarily have a minimum maximum value that's the same as for shelf 2 or for shelf 3 or for shelf 4. So because of that, in order to make sure that when I do plot shelf 2 or shelf 3 or shelf 4, I need to make sure that my entire area that I have available to me for plotting has enough room, essentially, for all the other cereals. So because of that, then, I need to control my x-axis limits, my y-axis limits, my z-axis limits. Where I say simply, let's find the minimum of all the sugars. Let's make that the smallest value on the x-axis. And then the maximum of all sugars as the maximum possible value for my x-axis. And I combine them together, and we use xlim just like what we would do with the plot function. Do the same thing for ylim, same thing for zlim. And so let's put this all together. And here's my plot. I didn't draw needles on it, but you could. And I didn't draw grid lines, but you could as well. And again, this helps you see certain things. Let's see here. You can see, for example, sugar now is, if you see where my mouse is going up and down, sugar is on this axis here. And you can see how all the, excuse me, the red dots essentially are kind of in the bottom half. And remember what we've seen before is that the sugar content seemed to be rather high for shelf 2. That's what red is for shelf 2. And you don't have any low sugar content cereals. And we see that in this plot. Okay, so those are 3D scatter plots. And I guess too, if you're really interested, I do in my code in my program, I show you how to do 3D plots in with three other packages. You're not responsible for those, but they're kind of interesting to see. Okay, let's move on to page 21 if there's no questions. Okay, so so far what we've seen are a variety of ways where we could get maybe up to 5 variables, maybe 6 variables on one plot. But what happens if you want to go higher? Well, that's where we have to use other kinds of plotting tools. And so we're going to talk about 4 different ones where we're going to focus on 3 of them. The first one that I'm going to talk about, I don't want you to ever use it, but the reason why I'm presenting is because you often see it presented, but you often don't see people say why it's not good to use. Okay? This first one is called a Chernoff faces plot. I think it's easiest to see what they are by simply taking a look at page 22. So this is with the serial data, and each face that you see in this plot is an observation. Remember, we have 40 serials. Now, characteristics, or the way that you represent variable values on one of these plots, is to have them correspond to characteristics in the face. So for example, and this is not the case here, but you can imagine, let's say, sugar corresponds to the size of the eyes. So very high sugar content cereals, you can see, can have very, very large eyes. Low sugar content cereals have very small eyes. And maybe mouth size corresponds to fat. So if you have a smiley face, a lot of fat. If you have a frown, not a lot of fat. That's how you incorporate many, many possible variables into one plot by making them part of a face, a characteristic of a face. Now, the problem with these plots is that it's hard to judge, let's say, one variable, compare one variable to another. So, how big, for example, is an eye, in terms of, how should I say, a big eye versus a smiley face. How can you judge, whether or not one is, let's say, the maximum value or another one's the maximum value? It's hard to make comparisons across the variables. There are better plots that do that. So that's why this plot is not very, very good to do. But I do have a little bit of an interesting story behind the use of these plots. The first time I saw these plots was a good friend of mine in grad school told me that he was using these plots to help pick grad schools to go to in terms of departments of statistics. And so what he did was he collected a whole bunch of information on schools. So you can imagine, let's say maybe he collected information on 40 different departments of statistics out there. And he had each characteristic of face characteristic correspond to an important part of that department, such as, let's say, number of faculty, number of courses that they have. And you can think of all the other things, when you're searching for grad schools, what will be important. You can think of those as variables. You get a multivariate data set to compare schools across each other, and then do a plot like this to see, well, which, to have a better understanding of which schools might be best. And so he actually used a plot like this to pick Kansas State. And I always joke with him that probably the Kansas State face looked like this. This is Dallas Johnson, the author of one of the 3 books that I recommended for this course, who is now a retired professor at Kansas State. So at the time, he was the department chair. And so I always said to my friend, his name was Chris, I said, I bet the K-State face looked just like Dallas, and that's why you picked Kansas State. Anyway. Now, a very similar kind of plot that's much better to do, you get the same kind of information out of it, is called a star plot. Some people might call these sun ray plots as well. The key is that you're still going to have, let's say, one of these faces. In this case now it's going to be a sun, or you could say it a star. You're going to have a star correspond to an observation. Characteristics of the star correspond to particular variables. Okay. Now, I think the easiest way to explain this, let's not go there yet. Now, essentially, you can imagine, let's say, if you look at a star in the sky, you see, to some respect, let's say, rays extending out from the center of the star. Well, in this kind of context, each ray is going to correspond to a variable. Variables that are large observations that have a large variable value relative to other observations in the data set will have longer rays. Variables that have a variable that is a small value for a particular observation is going to have a small ray extending from the center. A variable that essentially would have the smallest would have no ray coming out from the center at all. Now let's take a look at an example. This is on page 24. I know it doesn't look like a star, but you can kind of think of it as a star. These are star plots. There's 2 different versions. You see one on 23 and one on 24. I prefer this version on 24. This is for the serial data set. Okay? And first of all, we have this legend that looks kind of like a pie chart. And what this is just telling you is that which part of the star corresponds to a particular variable, sugar, fat, or sodium. So, for example, let's see here. Let's take a look at observation number 1. I believe this was Kellogg's Razzle Dazzle Rice Krispies. Notice you do not see any red there. That's because there was no fat in the cereal. But you do see some green there, and how far that green extends out is proportional to the value of fat. The value of sodium, proportional to the value of sodium in comparison to the other observations in your data set. So you can kind of think of, this is as far as it could go out in terms of what's shown in the key. You can see that this maybe goes out halfway. So maybe it has kind of a middle-of-the-road sodium value. Also, you see something with respect, a similar thing with sugar, kind of maybe middle of the road. Let's take a look at, remember the shredded wheats. Remember how we saw that they were kind of outliers. They had no sodium at all. Notice you do not see any green there. And they had very little sugar, very little fat. Well, you see that represented in this plot by having very small rays extend out from the center. Let's look at, let's see. Let's look at number 25. So, tell me about this one. What characteristics do we have about it shown on this plot? It has high fat, maybe the highest. Now, look how big that is. But it has kind of low to medium sodium and sugar. Let's see what that, I don't remember off the top of my head what that is in terms of which cereal. So I'm going to simply say cereal bracket, take the 25th row, since they're numbered 1 through 40 consecutively. And that happens to be post-morning tradition. So that is actually like a mucilix kind of cereal. If you ever buy mucilix, you know that they're often very high in fat content. It's because of the nuts. Yes.
Do you think this plot is useful? Only have like 1,000 observations?
Well, thank you for bringing that up. That eventually I was going to get to that. That imagine, let's say you have a case where you have 1,000 observations. How many of these stars would you have to look at? 1,000. So, in those settings, it can be very difficult to use these. But you can see if you have a small to medium-sized data set, this could potentially be useful. Okay. So overall, what are these plots used for? Well, as you can see, is that they can help detect outliers. And you saw that with 26 and 30, the shredded wheats. They stood out from the rest. Also what they can do, and this is more getting down the road, and what we'll cover in this course, is validate cluster analysis results. Often what we will be interested in this class, and the various statistical methods that we look at, is can I, let's say, group similar observations together in some way? Well, if observations are similar in some way, they should have similar looking stars. And so this can help validate then your grouping mechanism that you have. Okay, so let's look at formally how we can do these plots. Okay, so there's, again, as I mentioned, there's two different versions of these plots. They both use the function called stars. And if you remember, the cereal, sugar, fat, the sugar, fat, and sodium are in columns 8 through 10 of cereal. And so the only way that you can specify that that's what you want graphed is to put that in the first argument. There's not like a nice little formula argument that you could use. If you want, you can specify how many rows and how many columns of stars do you want. I specifically picked 4 rows, 10 columns because I have 4 shelves. So essentially I am actually representing another variable, shelf, on these plots because each of these rows corresponds to a shelf. So 1 through 10, the first row there is shelf 1. Draw.segments equal false. Well, I think it's easier to say what happens if it was true. If it's true, you get these nice colored plots. If it's false, you get these plots here that I think this is the way that star plots were originally intended. And you can kind of think of it in terms of better as rays extending out from the center by those lines that you see extending out from the center. If you say draw that segments equal false, this is what you get. And then key.loc stands for key location. So your legend. Where do you want it? And I've had a very difficult time figuring out how R says at 3, 12 where that corresponds to in our plot. Let me just do one of these real fast. So essentially, if you look at the help for this function, it says, well, okay, the 3 corresponds to where on the x-axis. The 12 corresponds to where on the y-axis. But in these plots, you don't see numbers 1, 2, 3. You don't see a number 12. You don't have an x and y-axis actual numerical scale. So essentially, what I always do whenever I do one of these plots is just pick some numbers out, maybe 3 and how about this? 3 and 9. Do the plot, and you can see how that obviously covers up one of the stars. So if I want to move it, I want to move it up. I increase the y, essentially the second value, which would correspond to the y-axis. And after maybe some trial and error, I'm off the star there. So sorry, that's the best that I can give you for how to tell R where to put the legend. And it's not a big deal, just some experimentation, you'll get it. So anyway, so as I said here, here's one of the types of plots. And again, we'll take a look at one of these here. So here's the center. This is observation 14. And you can see a ray extending out from the center, and they just happen to connect the rays with those lines. I prefer, again, the case where draw dot segments is equal to true. And so I actually also have color to help me differentiate between the different parts of a star. Okay. So let's look at interpreting this plot some more. Remember, my original research hypothesis was that the lower shelves tend to have a higher sugar content. Can you reach some informal conclusions about that research hypothesis by looking at this plot? What do you think? Shelf 2, especially, look at that. Moles have large black areas. Shelf 1, though, doesn't really too much. We do see some very low ones. So, I mean, when I first saw this, I was kind of surprised. So I was thinking the lower, the better for the little kids to be able to pull the cereal off the shelf. But instead, perhaps, those little kids, they're probably standing, and what they're going to see in front of them is shelf 2, not shelf 1. So maybe that's why that's done. We don't need to go through all these here, but which cereals tend to have high fat content? Yeah, I would say 8, 20, 14, maybe 25 too. So anyway, that's how you can use these plots to help interpret them. And also what you should do too on your own is compare what you see in this plot to what we've seen in some of the other plots. Again, that's going to help you understand better a plot like this versus maybe something that was simpler before you came into this class, a simple scatter plot. Okay, so we've already talked about the stuff that's on the top of page 25, or at least some of it, in that when you have a large data set, a plot like this is going to be hard to use, except if you can get creative in some way. What I mean by that, and I guess I'm actually highlighting this, what I mean by that is perhaps what you could do is summarize your data in some way over some of the other variables so that you actually have a smaller data set. So for example, with my serial data set, obviously I only have a sample size of 40. No problems looking at every observation. But what I could do is, let's say, form a star that has the average sugar, fat, and sodium value for shelf 1. Form another star that has the average sugar, fat, and sodium content for shelf number 2. So if there was some kind of easy way that made sense in a data set that you could maybe average over another variable, that's when you could still use these plots for a large sample size. Again, it's very data set dependent, but I at least want to point that out as a potential option. I say here too, with the place-kicking data set, I have 1,425 observations. That's too many for a star plot. But what I could do is average over all the variable values for each kicker I wanted to. And the number of kickers, I think, is about 40. Okay. So that's a star plot. Those are kind of fun plots. Let's take a look at what I think is my favorite plot for plotting multivariate data. It's called a parallel coordinate plot. Still remember when I first saw these plots. I was never taught these plots when I was in grad school, but shortly after grad school, I attended a all-day workshop on data mining. This was about 2001, 2002. That was when data mining was first becoming like, wow, what is it? And so we had a workshop at one of my STAT conferences, and I attended it. And when I saw these plots being demonstrated, I was like, wow, this is so cool. I can represent so many variables. I can get so much information out of one of these plots. And that was actually the only thing I got out of the whole short course. I actually left early because it was so bad. So a lesson to you, when you pay for these short courses, you might be paying $400, $500 or whatever for a short course. Make sure you do some investigations into the author, or not the author, the presenter, to see if this is a person who knows what they're talking about, who's well respected in the field, and hopefully also maybe you can somehow get an idea if they're a good presenter or not. I did not do that, and I was out. A lot of money for getting this parallel coordinate plots out of it. So anyway, here's the basic description of what one of these plots are, and then we'll take a look at an example. Imagine that maybe you have 10 variables, and they're all, to make it easy now, let's say that they're all quantitative, they're continuous variables. What you could do is create a vertical axis for each of the variables, so like a y-axis. Create like a y-axis for each of the variables. Rescale your variable, or rescale each of the variables so that the smallest value that's represented on that y-axis for a particular variable, or the bottom, sorry, let me start over. The bottom of a y-axis for a particular variable corresponds to the smallest possible value in that data set. The top of the y-axis for a particular variable corresponds to the largest value of that variable for that data set. Okay? So you can imagine that maybe you could plot, let's say, points for every single one of your 10 variables along all the 10 y-axes that you have drawn out. Now, since all 10 y-axes correspond to the same observations, how about you simply draw lines that connect the observations from one axis to another? That's called a parallel coordinate plot. Let's take a look at an example. This is for the serial data set. So, obviously sugar, fat, and sodium are 3 main variables of interest. I also included the ID variable there so we have a better idea of what the observation number is. And then I color-coded the lines that you see there corresponding to shelf number. So let's take a look at an example. Let's take a look at the bottom ID corresponds to ID number 1. Top one here corresponds to observation number 40. Okay? And so observation number 1, if we follow the line to the next y-axis, we see it hits right about there. So what that says is that for observation number 1 sugar value, it's kind of middle of the road. relative to all the other observations in the data set. And then if I keep on following the line, sorry, I'm getting off the line, down here, we see the fat content is as small as you can get. And if you actually look in the data set, you'll know that this is fat equals 0. And then, if you could keep on going here, and I'll explain how I know this later on. The sodium's kind of in the middle, if you were to be able to follow that line. So you can see how, to some respect, you are limited with how many variables you can actually put on the x-axis. But, of all the plots that we've seen so far, this might be the best overall for being able to view multivariate data. You can get a lot of variables on that x-axis. And the key is to understand that, generally speaking, with these plots, what we see down here is the minimum value for a particular variable. What we see up here is the maximum value. So all the variable values are rescaled. Notice you don't even see a y-axis numerical scale because everything's rescaled, because everything's relative to one another. And, especially let's say if you're looking for outliers, well, that's what you're interested in. Outliers, you're looking relative to one another, which observations stand out. If you're looking for trends across in a plot like this, what you're doing is you're looking for, well, are there certain observations that tend to have, let's say, low sugar values but high fat values, maybe low sodium values. And you can follow the trends or follow the lines that you see in this plot to help see if maybe certain observations fit that pattern. Okay, are there any questions so far about the general sense of what this kind of a plot's showing you?
Does this work very well if you have a lot of observations and maybe you get a ton of lines if you
This can be then one of the issues, and there's different ways that this is handled. And I guess we can talk about it now. Imagine a setting where you have a lot more observations. We only have 40. What can happen is that observations can be buried on top of, or beneath, I should say, other lines. And so that can be a problem. But there's what's called brushing that you can do with these plots. Not with this particular plot, but what you can do with, I will show you shortly, with another plotting function is you can brush a set of lines, which means is, let's say, especially if I have an ID variable here, I can, let's say, highlight those bottom ID values. So let's say maybe the bottom 10. And immediately throughout the rest of the plot, those observation lines will be highlighted. And so that's one way to get around it. Another way to get around it, which I don't talk about in my notes, and you're not responsible for, is that when you have lots of observations, simply what's the word I'm looking for? I cannot think of the opaqueness of the lines represent how many observations a set of lines represent. So if you have something very opaque, meaning that there's not a whole lot, it's going to be very light. If there's a lot of observations, it's going to be very dark, the set of lines. So that's another way to represent that. Unfortunately, we can't spend days on these kinds of plots, so that's why I just decided to cut that out of the lecture notes. So anyway, so the main function that you will see used for these plots is one called chord for parallel coordinates. It's in the mass package. If you're not familiar with what the mass package is, and I would expect probably a number of you are not, this stands for Modern Applied Statistics with S. This used to be the number one, the name is actually the same name as a book, which was the number one seller for how to use R for a long time, but the authors haven't updated it for about 10 years. But all the functions that they wrote for their book and the many editions of the book are all contained in this mass package. And this mass package is automatically installed by default when you install R. So you don't need to download it. but you will still, if you want to use stuff out of it, you still need to say library, parentheses, mass, and parentheses. Okay? Now, there are other functions that can do these plots too. We will take a look at this one called IPCP. It stands for Interactive Parallel Coordinate Plots. It's in the iPlots package for interactive plots. It looks like the authors of this package have decided not to continue to improve upon it anymore, and because it looks like they're trying to put together a new package that hopefully, I guess, will be better. And so just a little forewarning to you is that, you know, a few years down the line, this package might not work very well, or there might be something better, I should say. And then also something I'm not going to talk about is something called GGPCP for Grammar of Graphics Parallel Coordinates Plots. It's in the Grammar of Graphics Plot 2 package, GGPlot 2. This is fast becoming a very prevalent package that people use for plotting. When I was told I was going to be teaching this course, I was hoping that I would have time to talk about this package, but I don't think we're going to have time in this class to talk about it. And the reason why I chose not to is because it presents a different way to do plotting than what we've talked about so far and what we will talk about for the rest of the course. So it doesn't fit well, but I don't know, if we have time at the end of the course, I can always talk about it. Anyway, so how can I do one of these plots? So of course I say library mass, and then although I've already did this, I kind of have this here as a kind of reminder. Let's create an object that has all the shelves, different colors for all the shelves in it. And then I simply say par chord is similar to the stars package. I had to say x equal, where's my data? Notice column 1 is the ID variable. 8 through 10 is sugar, fat, and sodium. The color of the plotting points is going to correspond to shelf.color. Put a nice little title on the plot. And then I'm going to put a legend on the plot. Does anyone remember what locator 1 corresponds to? It allows me to pick a particular spot where I'm going to drop in the legend interactively. Let's do it up here. And there we go. There's my plot. Not too difficult. Now, sometimes it's very helpful to be able to highlight kind of in a, how should I say, maybe an old-fashioned way, be able to highlight a particular observation in one of these plots without being able to do it, let's say, interactively, which I will show you shortly. And so let's say I want to highlight observation number 1 in these plots, in this plot. Well, I do exactly the same thing, but I need to have some kind of distinguishing characteristic about just observation 1. And what I decided to do was pick line width. And I'm going to make the width of the first observation to be very big. All the remaining observations, I'm going to make it the default of width of 1. So I'm going to repeat the number 1 number times 39. Just to show you that indeed that is. There we go. So notice I have a line width for every single observation in my data set. And if I highlight this, I get the following. So that's how I knew, for example, that I had a observation 1 went up to a middle sodium value. Note that this is not in the notes, this part right there. This also then leads to another potential problem that you can have with these kinds of plots. And that is when you have a lot of observations that are intersecting one of these y-axes, one of these vertical axes, intersecting at the same point, it's hard to determine sometimes then what happens then on the next y-axis. Where does a particular observation go? So what we see here, for example, with the fat, let me actually jump over here to Word so I can write on the spot. What we see here for fat with observation number 1, we see a whole bunch of points with the same color going right here. So how do I know then, is the observation coming up here? Is it coming there? Is it coming there? Or where is it going? Well, the only way that you know is through somehow if you highlight that observation just as I showed you. Then this leads into a further discussion then of what happens if you have some discrete variables. Let's say you have a 0 or 1 variable. You're going to have a lot more of these problems because all the points will either be up here or down there. If you had a 0, 1 variable, a binary variable. If you have some kind of discrete variable that has, let's say, 3 levels to it or 4 levels to it, you might have these kinds of same problems too. So there are limitations. There's some ways to get around them, as I showed you with respect to being able to highlight, but there are some limitations. Overall, this plot's best when you have, let's say, continuous variables and you don't have an extremely large number of observations. Okay. So again, why do we look at these kinds of plots? Again, we are looking for particular trends. You might be looking for particular outliers as detected by these plots. So for example, remember, I think it was observation 26 and 30, the 2 shredded wheats that had very low sodium. That's where they lie. And you can see in this plot that they tend to have relatively low fat and low sugar content as well. We've seen this with other plots too. Sorry, I'm telling the same story over and over again, but I'm doing this on purpose because I want you to be able to see what you can get out of one plot and compare it to what you can get to another plot. Often you get the same kind of information. We also see, for example, we have some high fat content cereals as well. We've seen those too in the past, right up here. That's what those observations are, that have the very high fat content. What about the sugar content for shelf 2? What distinguishing characteristic about this plot tells us the same thing that we've seen before? The red lines tend to be higher for the sugar vertical axis. And you see that there. And it's really easy to see that because, let me jump over here to Word so I can write on it. I mean, we can see this right here. There's no red down here, except for now with my pen, but the red is up top. And so we see a particular kind of interesting trend. Now, if you look for other trends here, to be honest, it's kind of hard to see them. I don't really see anything else that's popping out similar to like the sugar or like those outliers that I've mentioned. Okay, page 27, there was one little, I guess, kind of a typo that I want you to fix. See the stuff I have in blue? Please change the value of 0 to lowest value and the value of 1 to highest value. So let's look at how we can use this IPCP function to do these kinds of plots as well. So it's in the iPlots package. This is a package you will have to download. And simply I say with IPCP vars for variables, I specify my particular variables, and this is what comes up. Notice a new window outside of R pops up. This uses a link to Java to do these kinds of plots. And let me remove some stuff here. There we go. Okay. So, I know it's a little bit hard to see, but you see, if you follow my mouse, ID, sugar, fat, and sodium. Now, the reason why I bring this particular function up is that this allows you to do this thing called brushing that I was alluding to earlier. So if I want approximately the first 10 observations, if I want to see where they are throughout the whole plot, I can just with my mouse left click on a certain area by in this case the ID variable, and just kind of drag down, and then when I release, look what happens. They're highlighted in red. So you can see where particular observations are in the plot. Instead, if you want to see, well, what about these high fat values here, these high fat cereals? Do they maybe have high sugar content? Do they maybe have high sodium content? Do we see some kind of trend that's coming out? Well, what I can do is just left click on this, drag my mouse, release, and now you see just highlighted those particular cereals. How about the 2 shredded wheats? Do the same thing, and you can see how they're highlighted there. So again, that can be helpful to determine, to see particular trends throughout the plots. Now, in order to, let's say, get this plot into, let's say, a Word document or make some kind of, or maybe even save a file out that contains these plots, you can't do the same things that we've done in the past. For example, this plot here, I could just simply copy to clipboard as metafile file, bring it over to Word. Instead, what you have to do, at least the only thing I know how to do, I guess there's other things you can do, but I think the easiest, especially if you have a Windows computer, is to use the snipping tool for Windows. If you're not familiar where that's located, it's, if you go under Programs, Accessories, Snipping tool right there, if you've never used it before. And notice how my whole window there kind of become grayed, kind of a little lighter, because that's telling me, okay, it's waiting for me to highlight a certain area. So I'm going to highlight around my plot. And now, up in my snipping tool window, I have my plot. And I can simply now, let's say, bring up a new Word document and paste it. Essentially, it's like if you've done screen captures before, it's just a way to do that. Hopefully you've seen that before. If not, your life might have been a little bit more difficult in the past. I think it's essentially print screen, but it's just, sorry, I don't know the details about it, but it just allows you to highlight a certain area. I used to always use print screens until I came across that. I think it might have came out with Windows, let's see now, we're at Windows 8 now. It was before Windows 7. What was before Windows 7? What's that?
Vista.
Vista? I think it was XP.
XP was the good one, and Vista was the lousy one. So it was okay.
Thank you for the Microsoft history. But maybe this is, you shouldn't say this out loud. I like Microsoft products, and I like the snipping tool. Anyway, okay, something else you can do that's kind of cool with this plot is that you have a way that you can add some information to the plot. So if I go under View here, I can put PCP over box plots. And I'm sorry, let me just do something real quick. So now notice there's nothing highlighted right now. So if I do PCP over boxes, now I have box plots that help you see the variability in a context that all of you have seen before, like the Stat 801 class. And look what happens too if I, let's say, highlight, let's say, maybe the first about 20 observations. Now you see overlapping box plots. And that will allow you to judge, if you, in particular, if you have a particular variable that you're really interested in, judge, are there differences between two variables? I'm sorry, differences within a variable between two different groups. So that can be helpful. Okay, that takes us to page 30. Now, as I said, I really like these plots. And so much so that I've used it in somewhat different ways than what I've never seen anybody else use it this way before. Now, statisticians, and a lot of other disciplines too nowadays do this, they often do what are called Monte Carlo simulation studies. What that basically means is that you might, let's say, generate a whole bunch of data sets where you control certain aspects of the data set. Maybe, for example, you know what the mean of the data set should be. And then you, let's say, apply a statistical procedure to every single data set. Maybe, let's say, calculate a confidence interval for every single data set, confidence interval for mean. And then what you could do then summarize over all those data sets some important characteristics, such as how often is, let's say, the true parameter inside the confidence interval. If you're doing 95% confidence intervals, you expect 95% of the time. Okay? That's an example I mean by a Monte Carlo simulation study. Hopefully you've seen them before, but if not, that's what they are. A very, very useful tool to evaluate, in this kind of a context, what we do as statisticians, evaluate a statistical procedure. Monte Carlo simulation studies are used in other settings too. But anyway, when you do a Monte Carlo simulation study, what you're often interested in doing is examining, a whole bunch of what-if scenarios. What if my data came from a normal distribution? What if my data came from a gamma distribution? What if my mean was 5? What if my mean was 2 instead? So you have a whole bunch of different scenarios. And in essence, what you're doing is you're doing these calculations and creating a multivariate data set. So a lot of the graphical techniques that we talk about here can be used then to summarize your Monte Carlo simulation study. Now, I know especially the statisticians here, you've probably seen in papers big tables that show the results from a Monte Carlo simulation study. It's kind of often hard to make sense of everything that's in that table. Instead, if you graph it, you can make a lot more sense. You can see trends that are developing. So, I want to give you an example where I've used this idea of graphing results from a Monte Carlo simulation study, in particular using something very, well, it is a parallel coordinate plot, but with a minor change to it. So this was a paper that was published in 2009 in the Journal of Statistical Computation and Simulation. It's not necessarily a Tier 1 journal, you could say, in statistics. It's a Tier 2 journal, kind of middle of the road. And what I wanted to do was I wanted to evaluate 4 different ways to fit a regression model, essentially. I'm not going to, it was a fancy regression model, but for our purpose, just think of it as a regular old regression model. 4 different ways to evaluate a regression model. 4 different ways to fit a regression model. And in each case, I want to estimate the slope coefficient. I want to compare the slope coefficient, it's called beta hat 1, from one method to the next. Ideally, for all methods, I would like to have exactly the same beta hat 1. But as you'll see, that didn't happen. So I simulated a whole bunch of data sets on, in this particular case, it was actually just one situation. I simulated a whole bunch of data sets, and I got a data set that looked like this. I had the 4 different estimation methods. Not important to know what these methods represent. They just have 4 different names. I have a whole bunch of simulated data sets here, and then I graphed the results. And this is what I got. We're running out of time here, so I'm not going to be able to go into all of it, but this is actually a screen capture from my paper. The right side, you see the parallel coordinate plot. What's one characteristic about this parallel coordinate plot that's different from what we've seen so far?
The scale is different.
The scale is different, yes. Because these individual, alike, random, and different, they're all measuring exactly the same thing, this beta hat 1. I had to get into the PARCORD code and change it so that you wouldn't see the rescaling. Because now it allows you to see variability. Notice the individual method, the variability in the beta hat 1s, is small relative to the variability in the different method. And in fact, that tells you, because in statistics we often want smaller variability, that tells you stay away from the different method. We are out of time, so I can't get into it more right now. Are there any questions? Okay, that's it for today.